Hey, Banana Data Podcast listeners! The podcast is currently on a break between seasons, but we don't want to leave you hanging in the meantime. Today, we're bringing forth a special episode in the form of a compilation of all our past In English Please segments. If you're unfamiliar with our content, these In English Please segments are quick explanations of complex data science terms, processes, or phenomena distilled into easy-to-understand concepts. Think of it as your data science encyclopedia. Here is part one of a two-part series of In English Please. To kick us off, Will, one of our hosts from season one, is going to explain federated learning in English.
Can you describe to me in English, please, federated learning?
How familiar are you with SGD, stochastic gradient descent?
Oh boy, I know that it means reducing something.
Reducing something, that's all you need to know. Kind of. So in general, the idea for our listeners at home, right? So much of the AI ML space is about prediction. And when we try to predict things, we're trying to do supervised learning. So we already have some historical training data. We're trying to learn from it. So when you try to learn from it, we're trying to fit some sort of mathematical function. And so when you're trying to fit a mathematical function, one way you can fit that function is through this process called stochastic gradient descent. And so this gradient descent idea is really important. The idea is that we have some parameters that make up our model, so like some numbers. And we're trying to find the right numbers because when we have the right numbers, that's going to lead to some minimization of our error. So really, you could sum up much of supervised machine learning as just that, trying to find the right numbers, the right parameters of a mathematical function that are going to minimize error. And lots of smart people spend lots of time thinking about how you do this. But the idea of gradient descent is that you could take a partial derivative. So if you're not familiar with, if you haven't brushed up on your calculus recently, don't worry too much. But in general, you could think of this, the classic examples. You're standing on the side of a mountain and you want to get to the valley. Why the valley? Because it represents the minimum elevation. In this case, we're looking for the minimum of the error. So if you want to get to the valley, you just look around, you see which is the steepest direction down. And then you take a step in that direction. If you keep doing that, in theory, you'll end up in the valley. And so this is the idea with gradient descent. You keep taking small steps in the direction of the gradient in an effort to minimize your function's error. So far, so good?
So far, so good.
Okay, so oftentimes the way this works in machine learning is that you have all of your data stored on one central server, one central computer, and you do all of your training then in there. The idea with federated learning is that data does not have to be aggregated. So in the paper that I read, Google was using Android phones that are, spread out throughout the world that all contain individuals' data. And so the idea or the promise of this, there are several, but one is that if I care about my data's privacy, going back to our previous conversation, I don't have to agree to share that data with Google or with anyone else. I can keep that data about me on my phone, but nevertheless, Google can, or someone, can learn from that data. So the way it works is your data will stay on the phone, but this model exists on some sort of central server. And remember, a machine learning model, it's just like a bunch of parameters, just a bunch of numbers. So we have these parameters that live on this central server. Those parameters get pushed out to phones, and then the phone says, okay, this is the current state of the model. Now I'm going to look at Trevani's data, which is representing supervised learning instances. I'm going to look at Trevani's data and see what cases I predict correctly according to the model's current state, what cases I predict incorrectly according to the model's current state, and I'm going to learn from that using gradient descent. After gradient descent occurs, now Trevani's phone says, hey, I've got some updates to these global parameters. Like, hey, Mr. Model at the central server, I've got some updates for you. So once that phone gets back on Wi-Fi, those network updates are pushed to the central server, and this process repeats. So I think the promise here, in theory, one of the promises is that data never needs to leave your phone, right? So the data can stay local, the data can stay protected, but nevertheless, we can kind of build this global model. So it's a pretty cool idea.
Yeah, so it sounds like even though, my phone is sending something back up to the server, it's not sending anything about me. Exactly. Right? It's just saying like, hey, I put some more data into this model and I think I tweaked it. I think I got us closer to the valley. So here's the map, how I got down to the valley.
That's exactly right.
I love it. I love this analogy, Will.
So it's a pretty cool, pretty smart idea. Okay, listeners, now it's time for my favorite part of the show, In English Please. So Trevani, if you don't mind, could you please explain neural networks in English, please?
Sure. I'm gonna try this out here. This is gonna be fun. So When we talk about neural networks and machine learning, what we're talking about are systems that are meant to replicate the way that humans process input, right? So if I show you a picture of a cat and a dog, you have a set of rules in your mind that tell you how to understand those two things as different creatures, right? Now in machine learning, neural networks are going to accomplish the same thing by creating weights for those inputs that then become rules on how to process new information. So if you think about biologically, our brains have these individual neurons that are constantly analyzing inputs and firing off information according to the rules that we've taught them. And in a machine learning neural network that's a machine learning neural network, each neuron is essentially a mathematical function that then takes that input and produces an output. So these neurons are arranged in layers or groups, and so we can say there's like 10 neurons that are analyzing inputs in the first layer. So in that first layer or that first step of the model, one of these neurons gets an input that says, hey, this animal has a small pink nose. And that neuron is going to apply a set of rules or weights that determine, okay, well, this is about a 90% chance that this is a cat then. And so each of the 10 neurons in that first layer are going to send outputs to the second layer neurons, who are going to process that information according to their rules and then pass that information on to the next group of neurons. So it just goes down this chain of neurons or layers of neurons. And so the number of layers and neurons can be really large in some cases, like image recognition. But after applying all of these weights and rules through all the different layers, the model is going to give us a final output. Like, okay, this is a cat, and that's based on the rules and thresholds of the complete neural network that came before it.
Awesome.
I'd love for you, Will, to explain epsilon greedy multi-armed bandits in English, please.
Yeah, so last time we spoke about multi-armed bandit algorithms, and just as a refresher, these things provide us with a decision method when choosing between different strategies, where each strategy has a various and unknown reward distribution. So refer back to our previous podcast if you want more information kind of broadly about what multi-armed bandits are and what they do. But so the question we had was about epsilon greedy multi-armed bandits. And so again here, this idea of an epsilon greedy multi-armed bandit helps us determine how we should trade off between exploration and exploitation. So with an epsilon greedy multi-armed bandit, you pick some small number, which we call epsilon. So maybe that number is like 5%. So then what you do is you pick in this case, the slot machine arm with the highest reward distribution, and you keep picking that slot machine arm that you've seen thus far has the highest historical reward distribution. So say I picked slot machine 1 and it returned $10. And I picked slot machine 1 again and it returned $20. Now my running average of returns for slot machine 1 is $15. So I'm going to keep going back to slot machine 1, and I'm going to keep track of the running average of rewards from slot machine 1. But where that epsilon comes in this case we said epsilon was 5%. So 5% of the time I'm going to take a random action. I'm not going to exploit. I'm going to explore epsilon percent of the time. So maybe my random number generator tells me that it's time to explore, and I actually check out slot machine 2. And I pull the lever on slot machine 2, and I find I get a reward of $50. So now I'm comparing an average of $50 for slot machine 2 to an average of $15 for slot machine 1. So the next time when I go to exploit, which slot machine do you think I'm going to exploit?
2.
2, exactly. So the running average on 2 is higher than the running average on 1. So now I'm going to keep exploiting 2 until, again, epsilon percentage of the time, i.e. make a random shift, or the running average for slot machine 2 falls below some other slot machine that has a higher running average.
And that's the greedy part?
And that's the greedy part. So usually I'm greedy. Usually I'm exploiting.
I know, Will.
Fair enough. Usually I'm greedy. Usually I'm exploiting. But every now and again, epsilon percent of the time, I explore. And this is kind of the gist of it. There are many more sophisticated applications or methods here. But that's basically how epsilon greedy multi-armed bandits work. Last week, we were talking a little bit about GANs, and I think that's something where definitely for me and probably many of our listeners, we could benefit from a little bit more clarification. So, Triveni, I was wondering if you could explain GANs to us all in English, please.
Sure. So everything you need to know about GANs is in the title. GANs is an acronym that stands for Generative Adversarial Networks, right? And so the 3 words there actually tell you what you need to know. So the first thing is that these are neural networks And what they're doing is creating a distribution of data, or they're mimicking data that can be text, image, or even plain numbers, in the idea of generating new points that are, in theory, indistinguishable from real data. So, for example, there's this website called thishumandoesnotexist.com, right? And if you go there, you'll see photos of people. None of those people are real. All of those images have been made by a model using GANs. Okay, so what did GANs do to make these people? Well, in a general adversarial network, there are two neural networks, and they're adversaries of each other. So we have one network that's the discriminator, and that's very similar to what we already are familiar with in terms of classification. Here's some data. Predict for me whether or not this picture of a person is a real person or not a real person, right? That's the model that's going to say, okay, yep, I'm seeing that. Yep, I'm seeing a real person. No, I'm not seeing a real person. And then you have the second network, which is the generator. And that's the network that's actually creating these fake images. So the generator is creating a fake image of a person and feeding it into the same data that the discriminator is looking at, right? So we're adding in fake images into a data set of real images. And the discriminator is judging, yep, this is human, this is not human, or real or not real. And the generator in turn is seeing what the discriminator is saying and updating itself to better fool the discriminator, right? And so they're adversaries in that the discriminator wants to suss out the fake data, and the generator wants to fool the real data. And so the idea here is that we're using these GANs, one, to create different models of, or different distributions of data that we can then use to maybe do some better forecasting. This is very common in the financial services, and as we were talking about earlier, or in the case of these images, which also then kind of raises questions around, well, what's real, what's not real? If a model can't distinguish it, can we distinguish it? And in this sort of era of false information, what does that really mean? But essentially, the GAN model is working against itself to improve the data that it is producing for you. So it's not really predicting something for you. In fact, it's actually creating a distribution of data for you then to work off of. Will, can you please explain collaborative filtering in English, please?
Yeah, sure. So collaborative filtering, it's really a tool used in the recommendation system space. Collaborative filtering stands in contrast to content-based filtering. So content-based filtering, we'll just kind of talk on that briefly because that will give you an understanding of what collaborative filtering is. Content-based filtering means that you have some sort of content or metadata on the content that you're trying to recommend to someone.
So like Netflix.
Exactly. So if we're Netflix and we have things like the genre of the movie and the lead actor in the movie, these are features that we could use to recommend a movie to someone else. So that would be classified as content-based filtering. You're taking some content about the movie. I mean, what kind of movies do you like, Triveni?
I like Marvel movies, actually.
So the genre might be Marvel movies, and then what sort of lead actor do you like?
Oh, Brie Larson.
Okay, so in that case, we know the movie is a Marvel movie, and it stars Brie Larson. Triveni likes these two things, so we should show Triveni this movie. That would be an example of content-based filtering. So we're using content about the movies to make recommendations. In collaborative filtering, all we're doing is using the preferences of other users. So what we do here is we say, okay, here's Triveni, we're looking for a movie to recommend her. Let's look at Triveni's past history, and let's also look at Will's past history. Let's look at Anna's past history. Let's look at Bob's past history. And somehow we need to understand, is Triveni similar to Will? Is Triveni similar to Anna? Is Triveni similar to Bob? And so mathematically, we can do that by looking at things like Pearson correlation or cosine similarity. But then we find a bunch of neighbors or people that you are like in your past behavior. And then once we do that, it's pretty simple. We just say, okay, well, Anna really liked this movie, and Will really liked this movie, and Bob really liked this movie. And Triveni is similar to Will and Anna and Bob, and they all like this movie, and Triveni hasn't seen it yet. So, given that Triveni's past watching and liking history is similar to those users, we assume that her future behavior will be like them as well. So we're just going to recommend this movie to her. So that's this idea of nearest neighbor recommendations using collaborative filtering. It can get more complicated looking at things like matrix decomposition, But in general, the basic idea of collaborative filtering is looking at past behavior of other similar users and then making recommendations based upon those users. All right, so now it's time for everyone's favorite part of the program, In English Please. So in this section, we explain complex data science topics in English. So Triveni, could you explain cloud computing in English, please?
Well, when we think of cloud computing, you might think of, rain clouds or stormy days, but that's obviously not what we're talking about here. Cloud computing is essentially doing some sort of work or data storage or anything really on a remote machine. So what do I mean by that? Well, a lot of us probably have laptops and desktops of our own. When you're working at your own laptop, you're, on premise. You're using the computer in front of you and you're using its resources. But let's say I'm working on a project that has a ton of data and a lot of heavy processing power is needed for it. Well, instead of going out and buying a brand new computer for $7,000, I instead can rent someone else's computer to run my program on, right? And that someone else is often a cloud service provider. So what does that mean? Well, you think of Amazon or Google. So they say, hey, I'll let you rent my server for 1 cent an hour, and you can run your program on my computer. And because it's remote, I'm going to have to connect to it through a stable internet connection. And in that way, we say you're working in the cloud, right? So if you've ever worked on a Google document with your colleagues or friends, you're doing work in the cloud. You have a shared document or something in a remote server where you're all accessing it individually through your own connections. And so now what does that server situation mean, right? Is it literally one computer that everybody's pointing to? No. What we have are actually giant factories and warehouses full of servers where people can ping in and get cloud computing power from anywhere in the world. So not only are these centers distributed both widely in terms of the world geography, also internally in each state or in each place, you'll have multiple servers to help route traffic from people to servers that are closest to them. Again, because it is an internet connection, you want to be as close as possible to your servers that you're using for cloud computing. So cloud computing, in a nutshell, is allowing us to do work or data storage or whatever it might be on a remote computer without having to go out and buy all of the actual hardware needed for that processing power.
Very cool. So cloud computing allows me to rent resources that I might need in kind of a scalable fashion wherever I might be on the world.
Yeah, that's actually absolutely right. Today, Will, can you please explain BERT to me in English?
Yeah, so BERT stands for Bidirectional Encoder Representations from Transformers.
Wow.
So we've got our work cut out for us today. But the audience can think of this as a neural architecture for language modeling. So we're in the NLP space here. And again, BERT was really a major step forward in us being able to understand language computationally. And so there are a bunch of big contributions here. So the first one that jumps out at me is pretty cool is this idea of access to data. So BERT is what I would call both a unsupervised and a supervised learning program. So to do this, they basically can just scrape all of the text on the internet. So in that way, it's unsupervised. You don't need to go through with Amazon Mechanical Turk, for instance, and actually label data. We can just take books, blog posts, whatever text has been written that we think is reasonably coherent English, we can use that. And then for the supervised piece, the way we accomplish that is by masking words in a text. So if you think about the sentence, Will made a deposit at the bank and then he biked home, we might mask or take out words to help train this model. So we might actually say, Will made a blank at the bank, and then he blank home. And so in this case, we've taken kind of an unsupervised way text that exists on the internet, and then we've created a supervised learning problem where we know the true answers are deposit and biked, but we need to learn them, quote unquote. And then two other ways in which BERT really contributed to the NLP space. One is attention, and the other is bidirectionality. So in terms of attention, this is a way for a natural language model to essentially consider context. So if we think about, Will made a deposit at the bank and then he biked home, who do you feel like he is referring to in that sentence?
Will.
Will, that's totally correct. So it's obvious to you, but in a natural language system, that's not super trivial to implement and understand. And so the idea of an attentional transformer, basically it's a computational way for us to, as we're looking at individual words in a sentence, also maintain an understanding of the other words in the sentence. So in this case, when the model comes to the word he, it's in a sense looking at all the other words, and it's really aware that he is associated with will. So that's, contribution number one. Contribution number two is the bidirectionality of BERT. And so as it says in the title, it's a bidirectional encoder. And so if you think about the sentence, Will made a deposit at the bank, if we're just reading from left to right, Will made a doesn't really tell you that much about what should come next. Whereas if we read from right to left, so bank the at blank, once you see bank, something's happening at the bank, now that's a really great clue to the fact that the correct verb there maybe should be deposit. So actually implementing this bidirectionality, it's not so trivial, because if you think about it, you can read something left to right and right to left. You can kind of cheat and look both ways. But I'll direct our listeners to the paper to really get into the weeds as to how this all works. But those are the two big contributions, I would say, attention and bidirectionality, and how BERT has really made a big leap forward in NLP space. Triveni, could you please explain random forest models to me in English?
Yeah, sure. So random forest models are a very popular form of algorithms that folks use across the board. And it sounds complex, but it's actually really quite simple. So when you think about a random forest, it actually breaks down into multiple little algorithms called decision trees. Now, a decision tree is something that we use every day. Should I wear my rain boots or not, right? And so, is it raining? Yes, then I should wear my rain boots. So these little decision trees actually add up to create a larger forest. So if you think about a data set where you're trying to predict, is this piece of fruit an apple or an orange? It's going to look at the color and it's going to say, is the color red or is the color orange? And based on the answer to that question, it will then make a decision about what prediction it's going to make. So in a random forest, we take all of those decision trees and we put them all together, put all those trees together into a forest, right? Literally. But the random part comes from using random subsets of data and features for each decision tree. So by doing that, you're actually preventing overfitting because you're able to look at a wide swath of data in a lot of different ways. And then once all of these different trees have made their decision about, I predict this to be an apple versus an orange, all of those trees, their decision gets, averaged out or voted out to say the majority of trees are voting for apple over orange for this prediction. And so random forest is generally a really good model in that sense. So I generally suggest folks to try out a random forest as a baseline, especially because it can outperform a lot of other models and algorithms out there, especially when you have a lot of features.
That's all we've got today in the world of banana data. We'll be back in 2 weeks for part 2 of our In English Please segment. Until then, subscribe to the Banana Data newsletter and podcast. See you next time.